Okay, let's talk about the clutter now for a moment. The radar is sending signals in the surveillance area, and we have the targets of our interest, aircraft, vessels, cars, whatever, and we have also other objects which are not of interest for the radar. These objects are just considered clutter. And okay, the role of this clutter, this clutter is going to provide echoes, and they are going to interfere the desired echoes of our targets of interest. So let's study the clutter for a moment. There are several types of clutter. We can distinguish between point clutter, which is contributed by singular objects like large buildings or towers. Even a bird can actually provide a point clutter signal, and they are modeled like a target just by a radar cross-section. Other clutters are distributed, for example, surface distributed target, for example, sea clutter or land clutter. In this case, the power of this clutter depends on the surface of illumination provided by the radar. So actually, the clutter is modeled by a surface density of radar cross-section, which is expressed in meters square of radar cross-section per meter square of illuminated surface. So it is adimensional. It is often expressed just in dB. And the value is just the product of this surface density or backscattering coefficient multiplied by the illumination which has been provided by the radar, this surface of illumination here. Other target types are volumetrically distributed. It is the case of rain or snow or most hydrometeors. In this case, actually the contribution of this clutter depends on the volumetric area which is actually observed by the radar. And this is called the uncertainty volume. The uncertainty volume is just the product of the range resolution by the surface, which is or the surface front beam of the antenna, which is can be obtained by r squared multiplied by the solid angle of the antenna beam. So if we multiply the volumetric density of the radar cross-section of this volumetric clutter by the volume of uncertainty of the radar, we obtain the radar cross-section of this clutter in this case. Okay, to be precise, the surface clutter area or area observed by the radar depends on the resolution and the beam characteristics of the antenna. So in this slide we can distinguish in two cases: the range limited surface, illumination surface, or the beam limited illumination surface. In the left side, we are talking about a high range resolution radar. In such a way, the radar is only sensitive to a portion of the illuminated beam projected on the surface. So this contour here corresponds to the antenna beam projected into the surface. The antenna is not sensing the whole area at the same time because we have high range resolution, so we are only sensing a range resolution part of this area here. So we have the slant range resolution. It is projected to the ground range resolution here, this part, and this is the surface of illumination, and this is the resulting expression. If we have a low resolution radar, then the range is not determined, the range resolution is not determined the surface size. The surface size is actually a consequence of the beam of the antenna. When the beam of the antenna is projected obliquously with respect to the ground, we obtain an extension which is here modeled by this expression here, and then that's the resulting approximation of the illumination area, assuming this is approximately a square area, and that's the resulting expression. So surface clutter depends also on the model we have to use, depends on the range resolution on the radar, the incidence angle, and the beam characteristics. Now, if we have to detect targets in a seriously clutter-affected region, which is typically the first 30-40 kilometers of a ground radar, for example, we have to be careful with the detection threshold because we could end up detecting mountains, buildings, and things like that instead of the targets of interest. So we have to modify our radar in order to cope with this interference. One of the things that can be done is to use an adaptive threshold in the detection process. So in this case, in red we have here the contribution of the echoes of the clutter and targets. And okay, if we use a fixed threshold level, we would end up with a lot of false alarms. So in this case, the radar is able to, in some way, adapt the threshold of decision in order to actually increase the threshold when the area is contaminated or strongly contaminated by clutter. Even in the case we do that, we can still have some false alarms, and we may have, hopefully, detection of the targets of interest. Now, how to do that? How to provide an adaptive threshold? Well, there are different techniques to do that. A way to do this is with a spatial CFAR, constant false alarm rate detector. This is what this acronym means. So the design of the detector tries to obtain a constant probability of false alarm in certain conditions. This is a possibility. It is called a cell averaging CFAR. In this detector, what we use as a threshold is actually an arithmetic average or an additive average of the cells which are surrounding the one which is being actually tested. So we are now taking a decision on this central cell here. We are trying to say here to take a decision if we have a target or not. And instead of using a fixed threshold, we use an adaptive threshold which is obtained as an arithmetic average of the surrounding cells here. So the resulting of this addition is actually multiplied by a threshold adjustment parameter, this capital T, and then we take the decision. In certain conditions, with, in this case, Gaussian stationary interference, it can be demonstrated that the probability of false alarm of this system is constant. And this is actually the result. M is the number of cells, and T is the value of this adjustment parameter. So we can obtain a low probability of false alarm by proper adjustment of the system. Now, what happens if we have a target in this situation? Well, if the target is also Gaussian, then the probability of detection it is this one. Okay. Of course, this is an ideal analysis situation. If for example, the interference is not Gaussian, the behavior will not be perfectly constant false alarm rate, but okay, it is a practical approach to be used. Another approach to cope or to reduce the clutter impact on the radar operation is by coherent processing. In this case, we are going to exploit the difference in Doppler characteristics or the spectrum of the echo characteristics of both target and clutter. Most targets of interest are mobile targets, so they are going to induce significant Doppler, whereas on the opposite, most of the clutter is static, which means Doppler is zero. Okay, if we look at the signals, clutter is obtained with a constant phase, whereas the target the phase is changing from one pulse to the next one due to the Doppler shift. Then if we look at the spectrum, okay, this is what happens in the time domain. Clutter is constant, target is affected by the Doppler, so it's changing the phase from one pulse to the next one. Then if we look at the spectrum of the signals, clutter is centered at zero, usually, and the target, it sits on top of a certain positive or negative Doppler term. Because these signals are actually sampled every pulse, we use the pulse system to do that, in this case a pulse radar. We have to take into account the Nyquist criterion or the sampling limits induced by the pulse repetition period, this capital T. So the pulse repetition frequency sets the non-ambiguous range in Doppler, which is actually extends to 1 PRF, 1 frequency of repetition. So this interval here is non-ambiguous. If the target has a Doppler which is outside this interval, then it will be interpreted as a wrong Doppler. But anyway, it could be distinguished still from the clutter. So, and how is this distinction going to be made? Well, we have two possibilities. First one is a clutter rejection filter. It's a very simple filter which is designed to reject the clutter spectrum region, which is normally around the origin. In this case, we use maybe the simplest approach is a single canceller. In this case, we take one echo and we subtract the previous echo here. When we take this echo as a complex numbers containing or retaining the phase of the echoes, when this corresponds to a clutter, a static clutter, the phase will be the same and they will cancel each other. However, if we have a target signal here, because from one pulse to the next one the phase has changed, the subtraction will not be completed and will not be successful, and we will get a residual here which will indicate the target presence. So here we have the impulsional response in a digital system. This is often implemented digitally. And we have here the Z transform corresponding to the filter. So we see here that this filter is a notch filter, is a rejection filter which has a null just at the origin for zero frequency. If we look at the spectral domain of the filter at the Doppler frequency range, we see here the shape of the filter. It's a null here at zero. Also at the alias frequencies of zero, which are the multiples of the PRF, 1 divided by t, 2 divided by t. T is the period of repetition of the pulses here. Here the target hopefully is not at zero, so it will go through the filter and can be detected. You have to take into account that if the target has a Doppler frequency, which is one multiple of the pulse repetition frequency, it will fall into one of the alias of the null of the filter, and then we will lose the target. This is the so-called blind speeds. So we have to be careful with the design of the radar, the pulse repetition frequency, and so on, in order to avoid blind speeds. Another approach, which is more sophisticated than the filter cancelling response that we have seen before, is the moving target detector. The moving target detector is actually a bank of filters, narrow band filters, which is actually used at the end of the receiver. And the objective here is dual. For one side, we want to reject clutter, but the purpose of the moving target detector is through spectral analysis, we want to measure or to estimate what is the Doppler frequency of the target. This will indicate the speed of the target, the radial speed of the target. How to do that? Okay, we use a bank of narrow band filters that process the signal at the output of the receiver in parallel. These frequencies are supposed to be, these filters are narrow band, and they are placed one on side of the other in such a way they cover, all these filters cover the complete non-ambiguous range of the Doppler spectrum. Now, the width of one of these filters is depending on the Doppler resolution we can obtain. And the frequency resolution, it is actually inversely proportional to the observation time duration. So if we have n pulses available from our radar, our time of observation is just the product of n multiplied by the period, t. So the inverse of this amount, which can be in the order of 10 Hertz, 20 Hertz, depending on the radar design, of 100 Hertz, depends on the number of pulses and the period of repetition of the pulses. Now, if we do this approach with a bank of filters, we have two options. We can actually build physically each one of these filters, or we can implement the bank of filters numerically with a discrete Fourier transform, which can be implemented with a fast Fourier transform, like in this case. So actually, the output of the FFT is equivalent to a bank of filters. This is the response for each one of these output of the FFT. So it corresponds to one of these filters, and this is the way it is oftenly proceed in this case on the implementation of the MTD. So finally, the Doppler resolution of the MTD system is 1 divided by the observation time, which is nt. Now, how to implement all this coherent processing? We have to take into account that this processing has to be done in real time during the radar operation for each radar resolution cell, so for each distance of the radar. So in the radar, we will distinguish between fast time, which is the echo delay time, which is here the horizontal axis, which is plotted here. And this is actually after one pulse, we collect all the echoes for different ranges. Then we transmit the following pulse and we repeat the operation again, and so on in this way up to n pulses that we collect with the radar. Then to do the coherent processing, we have to process this signal in columns. So we take for each resolution cell, so for each distance, we have to process the evolution of the signals for one pulse to the other. This is the domain we have in here. So, okay, we take the samples and then we can do MTI, resection of the clutter, and if we want, MTD. They are not incompatible, so we can do first, we can clean most of the clutter power with MTI, and then we can follow with an MTD in order to actually estimate the possible target radial velocities. And all this is done in real time. So the radar has a bank of memory here, which actually gathers all this information, and in real time we have all this coherent processing being computed by the radar. Okay, let's look at an example. That's a radar image, high resolution image, which contains a sea clutter, which is this level here, which corresponds to the sea surface reflectivity. And we have here a few targets. This is a large vessel, no problem to detect it. This is a medium fishing vessel, so it is also easily detectable here. But here, this is a very small boat, an inflatable boat, which is barely detectable. In practice, you cannot detect the target. You see it because there is a circle here, otherwise you cannot see the target. But then, if we apply MTI processing, in this case it's a sophisticated adaptive MTI, which actually takes into account the statistic parameters of the surface, autocorrelation of the surface, we can decrease the clutter level 20, 30 dBs in such a way. Now we have a very clean image when we can now detect even a very small target.